All right, good evening, ladies and gentlemen, and boys and girls. Welcome to a very special edition of our SETI Talks lecture series, which is a monthly lecture series that we do here at SRI International. My name is Bill Diamond. I'm the president and CEO of the SETI Institute, and I'd like to give a very warm welcome to many of our trustees who are here with us in the audience, some of my colleagues from the Institute. I also want to, of course, give a warm welcome to many of the familiar faces here in the audience who are regular attendees at this talk, and of course also a special welcome to those of you who are here for the first time. Could I have a show of hands of anybody who's here for the first time at one of our talks? Great, all right. Well, having had this close encounter of the third kind with the SETI Institute, we hope it won't be your last, and that we'll see you at other talks. Before I turn the podium over to my colleague Molly here, I do want to say the reason why this happens to be a very special evening and a very special edition of our SETI Talks lecture series. It just so happens that 35 years ago on this very day, the SETI Institute was formed. So that's pretty cool. I'm sure I was only 10 at the time. One of the original founders of the SETI Institute back in 1984 is here with us this evening and actually happens to be sitting on the stage here to my left, and this is the star of stage and screen, radio astronomer and SETI pioneer, Jill Tarter. So delighted to have Jill here with us tonight. As I say, we do have a very special program. One, just a couple of housekeeping things. If you have one of these, please be sure to put it in quiet or silent mode, or please, I told you never to call me here mode, whatever switch you have. That would be much appreciated. We're going to try and stick to a pretty tight schedule tonight because we want to be ending on time this evening. So we will have a period of about 15 minutes or so at the end for questions and audience participation. We'd love to do that. We have a mic here at the front, and we would ask you, if you have a question, come down. We would ask you, in consideration of your other fellow guests, to try and keep your questions short. We'll also ask our amazing panelists to keep their answers short as well, so we can get as many questions from you as possible. Without further ado, I'd like to turn the podium over to my colleague Molly Bentley, who is the executive producer and co-host of the amazing radio program and podcast for science we have at the SETI Institute called Big Picture Science. Molly?
Thank you. Thank you. This will be my podium for the evening, sitting here. I'm going to introduce each one of these scientists to you, and then they're going to give a short presentation, and then we will begin with Q&A. Victoria Meadows, otherwise known as Vikki Meadows, is an astrobiologist, and she is looking for evidence of biology on exoplanets. She investigates the habitability of these worlds and what atmospheric clues, such as oxygen, might tip us off to the presence of life on planets that are tens of light years distant. She is a principal investigator of the University of Washington's Virtual Planetary Laboratory and was a winner of the SETI Institute's Drake Award. Welcome, Vikki. Would you like to, should I introduce the other scientists first before we continue? Okay, I thought you might give your presentation. Jill Tarter is an astronomer who has devoted more than 40 years to looking for extraterrestrial intelligence. She is a co-founder of the SETI Institute, as Bill said, which is celebrating its 35th anniversary. She led the NASA SETI program and then its successor, Project Phoenix. Both projects attempted to find radio signals that would indicate intelligence elsewhere in the galaxy. Many people are familiar with her work as it was portrayed by in the movie Contact. Jill is now Chair Emeritus for SETI Research at the SETI Institute. Welcome, Jill.
Thank you.
Okay.
Yes.
All right, so I'm going to go first, and I believe I have a slide that should also be shown while I'm doing this. But so just to introduce myself, so I'm Victoria Meadows. I am a professor of astronomy at the University of Washington. I'm also the director of the astrobiology program there. That's a graduate program, so if you ever wanted to do graduate studies in astrobiology, you can come up and do that at the University of Washington. I'm also, the moment I'm chairing one of the science panels for a decadal survey, which is a big astronomy get-together where all the astronomers try and figure out what we're going to do for the next 10 or 20 years. And I'm leading the panel on exoplanets, astrobiology, and solar systems. So I'm very excited to be doing that, and I'm super excited that they clustered those three things together in particular. So I got into this whole astrobiology thing kind of by accident. I used to work at the Jet Propulsion Lab back at a time when an announcement came out and said, well, we're going to give a bunch of money to people who want to do some astrobiology. I had no idea what that was, but it turns out I used to be a Venus scientist. I used to study Venus. And one of the big questions about Venus that's always interested me was, how did it get so bad? I mean, how did it turn out so badly? So because of that, I was trying to understand how a planet loses its ability to keep water on its surface. And so when this big proposal came out, I put a proposal in, and I used my surefire way of winning proposals, which is to figure out what the sponsor wants and give it to them. And they had asked, could anybody please, try and get solar system science together with exoplanet science and maybe give us a chance of trying to understand what these worlds might be like in the future. That was back in 2000 when, we just barely discovered exoplanets. We didn't know if the terrestrial planets even existed, but my team, with a great deal of, reckless abandon, launched in and tried to learn about what terrestrial-type exoplanets might be like. And I'm very pleased to say that in May of this coming year, I'm going to get to put in a proposal to the James Webb Space Telescope to learn about exactly those objects. So it's been about 20 years in the making, but that is why I'm here, because I've spent 20 years thinking about these things. So just to introduce the concept, I'm Team Biosignature for the night. Jill's going to be Team Technosignature, but I'm just going to introduce what those things are. But I will say, as an astronomer, maybe you're like me, when I look out in the universe, there are two questions that I ask myself as I look out. First, I ask, are we weird? And are we alone? And the short answer is yes, we are weird. We absolutely know that now. We've discovered over 4,000 exoplanets outside of our solar system. And those planets, many of them don't even have an analog in our solar system. We don't even have planets like them in our solar system. There's this huge diversity of worlds out there, a huge diversity of what we call architectures, how the planets are all arranged. And so we found that the solar system actually isn't that common compared to the types of systems that we're seeing right now. So that's the, are we weird? Are we alone? So then this is where we're getting to the sort of main point of all of this, which is, okay, how do I tell that? And so Jill and I have different approaches to how we're going to do that. So I will talk about biosignatures. So biosignatures are simply, as the name suggests, signs of life. And so what we're looking for is essentially the global impact of life on its entire planet. Because if I'm going to try and see a signal that's, tens of light years away, it had better be a pretty big signal, okay? It has to be a very large modification of either the atmosphere or the surface of a planet. And so that thing is a biosignature. So as Molly mentioned, the best known biosignature, and still probably our best candidate, is abundant oxygen in the atmosphere. But the field of biosignatures has evolved quite a lot in the last 10, 20 years since I've been in it. We now know it's not enough just to detect the biosignature, we also have to interpret it in the context of its environment. What I mean by that is we need to learn about the planet itself, what it's like, so that we can say, yeah, that oxygen seems to be coming from photosynthesis, instead of, yeah, that oxygen seems to have come from an ocean that boiled off billions of years ago. Okay, so we now know there are these things called false positives, which is where the thing we're looking for, oxygen, is actually generated by something else in the environment. So back to this thing here. So this system here is called TRAPPIST-1. This is the TRAPPIST-1 planetary system. It has 7 planets in it. They're all about Earth-sized. They orbit around a tiny star. TRAPPIST-1 is only, about a half as much, again, as big as Jupiter. It's a planet-sized star. And because of the size of the planets and the size of the star, it's going to be one of the best targets, in fact, probably the only target that we can use the James Webb Space Telescope to look at the atmospheres of these terrestrial-type worlds. What will they be like? We have no idea. I mean, for all we know, they've all turned into Venuses because the star was very bright when it started out, or in fact, they may all be habitable. We don't know. And so we're going to try and learn about these planets and what they're like. As I said, we're going to put proposals in May. JWST should launch in about 2021, hopefully. And so basically, in the next 5 years, we are going to start the search for life elsewhere by trying to look for, first of all, do these things have an atmosphere? And then what's their atmosphere made of, and can we actually see signs of life? Now, that's one system. We get this one chance. But the great thing about this system is there's 3 planets in the habitable zone, so maybe there's 3 chances of looking for life there, so that makes it a good system all around. But I'll just wrap up by saying that's one system, so we start the search in the next 5 to 10 years. But beyond that, NASA is currently considering some pretty ambitious concepts. I'm very excited about them. So there's the Origins telescope, there's the habitable exoplanet surveyor, there's the large UV optical infrared surveyor as well. And so those missions that are just concepts right now, they're just designs, but very detailed designs, are currently being considered by this decadal survey I mentioned earlier. And we hope that in the future, one of those will be selected. The most ambitious one is LUVOIR. It would be great if that would be selected. We may not have the budget for it, but I'm kind of holding out for that one. I'd love to see that one selected. The reason is, with that one, we can get hundreds of planets, and potentially about 60 potentially habitable planets that are the right distance from the star to have liquid water on their surface. So instead of 1 to 3 chances up here, sometime in the next 15 years, we may launch a mission that will allow us to get tens of these things to go look for that. So I guess my point here is, I don't know if we're going to find biosignatures first, but I can tell you that in the next 10 to 20 years, we have finally gotten the science and technology together where we're going to be able to go and look for signs of life on other worlds.
Good deal. So I'm Jill Tarter and co-founded the SETI Institute 35 years ago. And it's a way to save NASA money. It was a really good idea. There were no civil servant positions available for SETI work. So we were getting all of our talent from local universities. And one in Berkeley, one down the road here, and San Francisco State. And at the time, indirect costs at these universities were astronomical. Some of you may remember that Stanford had a yacht funded by indirect costs. So Barney Oliver and John Billingham commissioned a study from a businessman at San Francisco State on a model where if we formed a nonprofit and had all of our soft money people become our employees, then we could set an overhead rate that actually reflected the cost of doing business, which was very low. And we did it, and I was the first employee, and I wrote a charter that was broad enough to encompass any of the different fields associated with the question of life beyond Earth. And it turned out to be such a grand model that last month, we just brought in our 100th principal investigator, now working at the SETI Institute. We have 100 PhD scientists who are studying all kinds of different things, including astrobiology and thinking about biosignatures. But what if, when you get those telescopes, Vikki, to study TRAPPIST-1, if JWST ever launches, there's wood here somewhere, right?
Get it better. It's wood
What
all
if
over.
this is what they see? Rather than those pretty artist concepts that you saw in Vicki's slide, what if we see this? What would you think? Might you think somebody's been engineering these planets, right? They should be different temperatures because they're different distances from their star. They should be have a great diversity, unless they all turn into Venuses.
Yes.
So I bring this slide up because we've been doing SETI, the search for extraterrestrial intelligence, for all this time. And we know that it's a misnomer. We actually don't know how to find intelligence at a distance. What we've always done is use technology as a proxy for intelligence. And then if we can find some evidence out there that someone has used technology to modify their environment in ways that we can see over vast distances, then we'll presume that at least at some time there were some intelligent technologists. So technosignatures is a term we're now using in addition to SETI because we're trying to think about how to do the search in more than one way. So we too are looking forward to those fantastic telescopes that we hope get built in the future because we want to investigate what they might see and how to interpret it. We may see some large astroengineering structures. We may also we will continue to do the kinds of radio and optical and now infrared searches that we've been doing. I'm particularly excited about a project called Laser SETI, which is the first time we will be able to look at all the sky all the time and be sensitive to transient signals. Till now, if a signal is there, either at optical or radio or infrared frequencies, it has to be persistent for us to be able to confirm and follow up and verify. But we're now thinking about signals and models for signals that might just be transient. Someone might be using a huge laser, where have we heard this, to accelerate a sail, solar sail, and that laser may cross our field of view, and it wouldn't be there for very long. But if we were looking in all directions all the time with enough sensitivity and ways of immediately verifying what we've seen, we could, in fact, find that kind of a technosignature. So we'll continue the radio searches, we'll continue the optical searches, and we'll push into the infrared as technologies allow. And who knows when we could succeed, but I will actually suggest to you that I have a better chance of succeeding first, because you've got to wait for NASA to finish JWST and get it on the sky. So we could succeed before you get there. I think it's a really interesting race.
Thank you. Thank you, both of you, and for throwing the glove down, because this evening's talk has been framed as a competition. Who will succeed first? Will it be the group that is looking for technosignatures or the group that's looking for biosignatures? And although it is not a boxing match, we should start with a verbal handshake, as they do the handshake that we do, because I believe that you both wish for each other's success.
We do.
That's right. So, however, having said that, I love that Jill just said, will probably be first. I wonder if we could let's talk about exoplanets for a moment, and there's a beautiful slide, and if you see us looking down here, it's because we have it in front of us. Thank you. And how the discovery of exoplanets, as Vikki said, that number is now more than 4,000, has changed the hunt for extraterrestrial life, both in the hope that it gives to finding technosignatures, but also biosignatures, and for which the first discoverers have won a Nobel Prize. The discoverers have won Nobel Prizes. Mm-hmm. And these exoplanets, as rendered by an artist here, are stunning in their diversity. They are water worlds, they are gas giants, they are dark worlds, they are worlds that rain glass and titanium. And I wonder if the technology that allows us to identify some of these physical characteristics of these worlds, that we get an idea just how varied they are, is the same that is telling us whether or not they might be habitable. And if habitable if you could distinguish between habitable, evidence of life, and life itself. Because you're not looking for life itself, I don't think. You're looking for evidence. If you could just talk about that, please.
So exactly the same way that Jill said the analogy was, it's hard to detect intelligence. I'm sure there's a joke there waiting to happen, right? But it's hard to detect intelligence, but technology is a proxy for that. We say if we detect technology, then intelligence must have built that technology. The same way, biosignatures are not life itself. They are the impact of life on its environment. Mm-hmm. And so, but that is a distinction when sometimes, when people say, oh, well, we found a planet in what we call the habitable zone. And what that means is that planet has probably a higher than elsewhere in the system probability of being able to support liquid water on its surface. So a colleague of mine, Kevin Zanley, who works at NASA Ames, you're probably aware of that place, he recently wrote this lovely chapter for a book I'm editing, and in it he described the habitable zone simply as light on water. Okay, and I thought that was beautiful and evocative, and that's exactly what the habitable zone is. It's the zone where we might see light on water. Okay, so I know a lot of people say, well, yeah, well, what about Europa? No light on water there, okay? So light on water is what we're looking for. And so ironically enough. Light on water might be what we actually look for, but we can only look for it with these direct imaging missions, so like the LUVOIR and HABEX that I talked about. They will enable us, LUVOIR in particular, HABEX may be able to do one planet that has an ocean, LUVOIR may get up to 8 to 10 planets that have oceans. We can actually look for the glint, we can look for the reflection of light off of the ocean of this distant world, and be able to see that as it moves around its star. So that would be direct evidence of light on water, which is what we're looking for. JWST, interestingly, is going to be much harder for us to tell whether the planet is habitable, whether it's able to support liquid water on its surface. And so we're going to have to try and infer things from, maybe water vapor in the atmosphere, or it turns out JWST is very good at telling you when it's not habitable. It's very good at telling you that, this thing lost an ocean, or, we could potentially see molecules in the atmosphere that tell us that there's no ocean on the surface. So it's two different things, and I haven't said it very clearly, but habitable is where life could possibly be there because we can see light on water. But an actual inhabited planet has life on it, and it will display the biosignatures. It will see these other things like surface reflectivity due to the red edge of plants, for example, or oxygen in the atmosphere, or the breathing of carbon dioxide in our atmosphere as plants grow and die. So we can look for those types of signals as well to talk about an inhabited planet.
More in a moment about those signals.
But actually, I want to add something.
Yes, and I'm bringing it around to you.
All right.
I'm doing a lap around what we're going to do. I'm coming back to you because what I want to ask Jill is, and then please expand if you will, that how the discovery of the exoplanets has changed the search for sophisticated extraterrestrial intelligence. So is it because it increases the number of planets that may be habitable, as Vikki said, and then that increases the odds of an advanced civilization? So in other words, is it a numbers game that is now tipping in your favor?
It definitely is. But what I wanted to start with saying is that, I don't know if you know this, Vikki, the whole search for exoplanets got started as a part of SETI. Right? When we were in the mid-70s and thinking about how to do this, nobody knew whether there were any planets. Nobody knew whether planets would be plentiful. And so we started holding workshops that Bill Barucki, among others, attended at NASA Ames, and that's where the whole exoplanet searching began, because we wanted to know where to point our telescopes to look for technosignatures. And so, yes, the numbers game has changed things immensely. In 2011, when the Kepler spacecraft announced its first batch of detections, those immediately became our targets. And now that Kepler and the ground-based telescopes have shown us that there are more planets than stars, every star, in fact, has a planet, we've then abandoned the focusing on the known exoplanets, especially Kepler's planets, which were all in one part of the sky and many hundreds of light years away. And we've just said, well, every star has a planet, so why don't we just start close to home and move out? And so it really has been a numbers game that's changed the way we do things.
Just to follow up on the numbers, so we were talking that the number of exoplanets now exceeds 4,000. How many planets or how many stars have planets, exoplanets around them? Does that number exceed in the millions? Are we talking about billions? What are the?
Well, there are 400 billion, give or take, stars in our galaxy. And if they all have a planet, we're talking about hundreds of billions of planets. Now, if they're all the right planet or the right kind of planet, the potentially habitable planets, that's going to be a smaller fraction of that. And Vikki's going to help us understand what that fraction is.
So you have your work cut out for you. I wonder if we could talk a little bit about the James Webb Telescope and actually how it works. So the idea is that you're looking for the chemical signature in some of these, around some of these planets or of these planets. And you do that by studying the ring of light. That's one way to do it, I understand, and you can correct me. When the exoplanet is in front of its star. At least that's the technique that I'm putting in front of you now. And I wonder if you could just explain to everyone how light can tell us anything about the chemistry of a planet.
Right. Okay, so yeah, so the ring of light, you're talking about the transit spectroscopy. So, so what we're doing with JWST is these TRAPPIST planets, not only is it special because there's 7 in this one system, but they all pass in front of their star. So they're all co-aligned so beautifully that they all pass. You get multiple transits at once. It's an amazing system. And it's nearby. It's 12 parsecs away. And so what we're going to do with this system is as the planet passes in front, you can imagine that it has like a little halo around it of atmosphere, and then light from the star passes through that atmosphere onto you, the observer. Okay, but as light passes through that atmosphere, molecules in that atmosphere are able to absorb wavelengths of light at places where they like to absorb wavelengths, and that leaves us with kind of a barcode of what is actually in the atmosphere. So that's what we're going to try and do with the TRAPPIST-1 planets with JWST. This is incredibly challenging because, again, you know, these are distant planets. I don't know if any of you have seen that beautifully evocative picture, the thin blue line. Have you seen the thin blue line of Earth's atmosphere? Mm-hmm. Okay, well, imagine we're trying to detect that on an Earth-sized planet passing in front of a Jupiter-sized star. So we're trying to pick out that tiny little difference and try and tell whether, you know, water absorbed down here, but maybe not up here. So, I mean, it's going to be a very challenging observation, but we think JWST can do it if we can reach the sensitivity that we hope it can. And so that's what we're going to do. So we'll look for the light passing through the atmosphere, and we will look and see if we can see the characteristic absorption from water vapor, from carbon dioxide. Carbon dioxide looks like we can do it in 2 or 3 transits. We only really need to watch the planet go in front of the star 2 times for us to be able to potentially detect carbon dioxide with that. So that is actually a slam dunk, relatively easy observation. So I'm pretty confident we'll get something out of these planets. And so if they have terrestrial atmospheres like the, you know, Mars and Venus and Earth, we all have carbon dioxide in our atmosphere. If these guys have carbon dioxide too, we should be able to tell that.
Can you give us a quick list of what some of the key chemicals are that you would love to find?
Right.
I mean, we could probably guess some of them. We've named some of them. Carbon dioxide, oxygen, water vapor by itself. I know that NASA's mantra is follow the water, but water vapor itself doesn't say that. It suggests habitability, but it doesn't suggest the presence of life in the way that some of these other chemicals might.
Right. It may not also suggest habitability and may not be there even if the planet's habitable. Water's tricky. Okay, so water, if you think about it, is really the most common polyatomic molecule in the universe. It's everywhere. As somebody once said, you know, this entire solar system is just squelching with water. It's on the giant planets. It's on, you know, but liquid water on the surface of a planet, that's the rare thing. That's what we have that's special. But there's water vapor in the atmospheres of both Venus and Mars and in other planets as well. So the sorts of molecules we're looking for, well, we kind of have an observing strategy. So that first proposal we put in May will ask the fundamental question, do these have atmospheres? Okay, because if these are a bunch of airless rocks, you know, all bets are off for our ability to actually detect life on there. It doesn't mean that the mole people aren't living inside. I didn't say that. Mole people. Okay, but we're not going to be able to detect them with our telescopes. Okay, so we need to have an atmosphere to maintain an ocean so that we can see that light on water eventually. And so we'll look for an atmosphere first. And one of the biggest, easiest things to look for to detect a terrestrial planet atmosphere is carbon dioxide. So we'll use CO2 as our test for is there an atmosphere there or not. And then we will look for things like water vapor. We can look for oxygen if it didn't come from life. So if this planet and these planets, the interesting thing about their star is that star was probably super bright when it was first formed. And it would have collapsed down slowly to its current, you know, 1.4 Jupiter radii size and gotten dimmer in the process. But when it was super bright, it could have potentially boiled off oceans and turned all of these planets into Venuses. Okay, so they might all have carbon dioxide, and a lot of it because they're Venuses. But because of that boiling off of ocean, we might be able to see when lots of oxygen molecules collide with each other, they form something called O4, O2, collisionally induced absorption. That is a very strong signal. We can probably see that, but seeing the oxygen from a photosynthetic biosphere is going to be much more challenging. So I don't think James Webb's going to see the oxygen from the biosphere, but it is going to see the O4, the collision of oxygen, which might tell us that an ocean was lost. And then the other thing we're going to look for is methane. And so methane, it turns out, on planets orbiting M-dwarf stars like TRAPPIST-1, tends to build up in the atmosphere much more readily than it does here on Earth. So even if there's a tiny amount of methane coming off the surface, we should get a pretty strong signal for that.
How much methane is coming off of Earth? We have a lot of animals that are producing methane. for
Right.
example.
So I don't know the actual flux number. It's like 10 to the minus something or other. But we have 1.8 1.8 parts per million of methane in our atmosphere. On these planets, we can build up, tens of parts per million, so, factors of 10 or so more. But the interesting thing is that the wavelength that James Webb is going to be able to observe the atmospheres, there's lots of very strong methane bands in there. So JWST is very good at CO2 and methane, so we'll definitely go after those two. And it turns out that on the early Earth, back before oxygen rose, CO2 and methane together might have actually constituted a biosignature. So that's a relatively easy thing for us to go after. So we will go after early Earth type life rather than photosynthesis.
And there's a relationship between the light patterns that you see coming off of these planets and their chemical signatures. Jill, if you were an alien scientist, not you specifically, but if one were on another
Some
planet,
days I feel like that.
okay, looking for intelligent life elsewhere, Earth would be an exoplanet. And I wonder what our signature would be for an alien scientist somewhere else, what our chemical signature might be, what the technosignature might be, what would we be giving off? And would that scientist conclude that our planet contains life?
Well, one of our signatures would be the broadcast radio and television that we have been generating for 100 years. Mm-hmm. So if you're within 100 light years, you could have access to that information, and that's clearly an engineered signal. Mm-hmm.
And remind us what some of those early signals were?
Oh,
or is it just, it's ongoing?
Oh, 100, we're talking about early television and radio, right? Howdy Doody and Long Ranger and all that good stuff. Maybe that's why they haven't responded. They don't like our programming. But the other thing you might see is smog and auto exhaust and carbon fluorides. Mm-hmm. You might see that for a period of about 40 years, you might have unwillingly seen nuclear explosions, the 2,000 or so nuclear bombs that we exploded around the planet. And you might possibly, if indeed we launch a lot more spacecraft into geosync orbit, you might actually see that as a disk or a halo. If you were actually to see it edge on, you might actually see all of the stuff we have in geosync, all of the trash that we have in space now. That might, in fact, be a detectable signature of technology on this planet.
Mm-hmm. And our chemical signature? There would be enough methane, there'd be enough oxygen, there'd be enough to say to a scientist far away that there is definitely life there. What about the possible signatures, the bio and technosignatures we've been talking about for extant life, but what about for life that is no longer? Is there a kind of signal that lingers for a civilization that is past, or for a life that, or for even very basic biological life, or life that is no longer?
I think from the biosignature standpoint, one of the interesting things about biosignatures is we've talked about chemicals in the atmosphere that we want to look at, but it turns out the actual biosignature is the flux. So it's how much of that gas is coming off the surface of the planet. So methane, for example, that when you pass water over basalt rock, it can produce methane, and that's got nothing to do with life. But it doesn't produce it at the same rate that life produces methane on this planet. So life produces methane at about 200 times more, 200 times a higher rate than water running over rock. And so it's that flux. So if you turn that flux off, it turns out that the methane would go away. It would have a relatively short lifetime. But it's that short lifetime in the atmosphere. It would react with oxygen and water and other things in the atmosphere. It's that short lifetime in the context of, remember I said detect life in the context of environment? If you put methane up into our oxygenated atmosphere, I can't remember its exact lifetime, but it's of the order of tens of years. So if you don't continuously produce it, it just goes away. So that is really what the biosignature is. The biosignature is, we're here, we're producing stuff, we're doing it constantly, and even though it's being eroded and taken away and reacted away, it's still there.
So it can't be a trace. You're really looking for an abundance of.
We're looking for an abundance, but we're also looking for continual production of it. That's what tells us. So when that life goes away, things collapse down into an equilibrium state, or closer to an equilibrium state, where you don't see those biosignature gases being produced. So I'm not sure whether we could see the remnants of life. It would kind of be like a ruined building that gets overgrown, kind of thing. It would not be there anymore.
We've been
Timing is
talking
important.
with this bias about life being biological. But in fact,
Yeah.
if we someday build machines and the biology goes away, the machines might still continue to broadcast, produce detectable technosignatures, build things, change the planet, even if there's no more biology.
I'd like to talk about false positives, because they affect both of you. It's something that comes with the territory. And I wonder if, Vikki, if you could tell us, are we able to distinguish, you said that these chemicals can be produced in different ways, and not only not from necessarily a cow on another planet producing methane, but let's talk about oxygen in particular, because, can you still hear me? Okay, it just seemed like the volume went down. Okay, thank you. Could you distinguish oxygen that was produced from biology from oxygen that's produced from geology? And can you just talk to us about how the role of false positives makes your job difficult? You have to stay alert, because there are many ways. I think you've identified 75 different ways that that we might have oxygen false positives. You don't have to name them all, but if you could give us an overview.
I don't know where you got the 75 from. I can think of four major groups. Maybe there's subclasses in there. But so I mean, originally we thought, you detect oxygen. We're the only planet with abundant oxygen looking around to the left and the right, right? And so we think, well, this must be the important thing. So in the past, about 10 years ago, we would have detected oxygen and then gone off to pick up our Nobel Prize. And that would have been sort of how we did biosignatures. And I have to say that even though it makes my job more challenging, I think what it's showing is a maturing of the field, because again, oxygen is an incredibly common atom in the universe, and just thinking that only biology could actually put two of them together was pretty naive. So what we found is that chemistry from light interacting with the atmosphere on planets can split up carbon dioxide and water vapor, both of which have oxygen in them. And potentially, we can end up in situations where the oxygen then recombines and is stable in the atmosphere. It doesn't react again. So photochemistry can produce can produce oxygen abiotically. So I would say it's not actually a downer, it's a good thing. We're more aware, as you said. Plus, we're now thinking, we're racking our brains about, okay, how can this planet fool us? And by being prepared for that, we can then say, okay, so it's going to try and fool us this way, but it's going to give itself away by doing that and that as well. So we can now predict, okay, if I see oxygen from an ocean that has been boiled off early on in the history of the planet, then I see this very dense oxygen atmosphere. I see the O4. I see no water vapor. I see no methane. So there's things that I not only see, but that I don't see, that I can then use as a pattern to say, this is probabilistically more likely to be ocean loss and less likely to be a biosphere. And that probabilistic is really super important. We're now evolving the field to the point where we're now trying to calculate probabilities for all of these things. So when we come to you and say, we found a planet with life on it, we will actually come to you and say, we found a planet where 80% confident it has life on it, right? So unfortunately, unless they send us modulated radio signals encoding pi, we are always going to be interpreting something that has that has potentially a false positive for it. And so the more we learn, the better we can get that probability.
You're not prepared to say anything like that yet, that you found a planet that has 80%.
Oh, goodness, no,
Okay,
no.
okay, just want to make sure. That doesn't
She would have
escape-
won then.
Well, that was my next question, is would 80% count in this biosignature versus technosignature? 80% confidence? I don't know if Jill would accept that. 60%, 50%?
Yeah, I mean, when you're
But
detecting a technosignature.
But other than going there and confirming it, we have to rely on probability. What to you would be a very strong signal that the signal is coming from biology? Would it have to be as high as 80%?
Well, yeah, I mean, that's something we're working on in this field right now. I think I would want 80 or 90% before I went there, but I'm pretty conservative. So, I mean, depends on what we finally come up with, and how, trying to circumscribe our ignorance, essentially, and what we can do here. But if I can counter Jill, she's going to find them first. I just want to say that this is a probability issue, right? And this is a numbers game. And I will say that the sort of biosignatures we're looking for, many of them were present over much longer time spans of the history of our planet than the technosignatures were. And so it's just a question, so Jill thinks she'll get there first because she has the equipment already, but my question, and I'm racing to try and build the right equipment, so I'm behind, but I have to say that if we're only looking at a relatively small sample in the local solar neighborhood, which is what we're currently looking at, the probability that we have pond slime, I think, is higher than the probability we have a radio telescope building civilization.
Yeah, but we can look for technosignatures to a much greater distance than you can look for biosignatures, at least through the predictable Louvre error. Because what we're looking for is something that's engineered, something that has gain in it, something that is potentially detectable over a much longer range. And so...
yeah, our signal's passive. Yours is active, potentially.
Right.
Yeah.
May I just ask you a quick follow-up on false positives for radio telescopes? And then be thinking about your questions, please, and if you'd like to come down to the microphone here, then we'll turn the questions over to you.
So of course, we deal with false positives every single day. We detect hundreds of thousands of signals and have to rule them out
Every day you do?
No, not every day.
Did she say every day, or was that just my ears?
No.
Okay.
We deal with these every day.
Oh, you deal with them every day.
When we write a paper, right, we say, okay, over this period of time was a couple 100,000 signals, and then we were able to rule out this, and this with various tests. Because what we do is we hear ourselves and our own technology all of the time. And so it's important to build a telescope. Actually, it's important to build an interferometer, which is what we've done with the Allen telescope array, because then you can use a test that says that signal is actually moving on the sky. It's a point source moving on the sky at sidereal rate, like the stars move, right? And that's not our technology. But false positives are something that we've gone through a couple of times.
Can you tell us about just one briefly that sort of knocked your socks off?
Yeah, right.
Halfway off?
And then I had to, it almost made Steph and I enemies at that, because I...
Can he confirm that? He's in the audience.
Yeah. So yeah, I was
chewing his knuckles, so perhaps.
I was unthoughtful. We were in West Virginia at the Green Bank Observatory. We detected a signal at 5 in the morning. It looked like, if you can imagine drawing a graph where frequency goes horizontal and time and intensity of the signal is vertical, it looked like a picket fence, right?
Oh, goodness.
Right? And it was clearly engineered. We always used to observe with at least 2 telescopes, but Mother Nature had done us in, and lightning had taken out a disk drive at the 2nd telescope. So we only had 1 telescope, so we couldn't do a differential Doppler comparison for the signal seen from the 2 telescopes. So all we could do is point at the target, a star, then we got the signal, then we point away, and the signal would go away. We'd come back, the signal was there. We'd go away in some other direction, the signal would go away. And this went on for hours. And I thought, I'm going to write a program, and I'm going to see if we have ever seen this particular spacing between these signals, that frequency difference, any time in the past at this telescope from some other direction on the sky. It's a clever thing to do. I wrote the program. I was too sloppy in my printout, and I I read it quickly, and I didn't see that, yes, indeed, we had seen that particular frequency spacing from a different part of the sky. And we kept observing until the star set. And at that point, we knew that it actually wasn't coming from the star, because the rate at which the frequency was changing was appropriate to a star that was rising to the zenith, not setting to the west. So we knew it wasn't actually coming from the star. And we went to dinner and did a bunch of internet research and found out that it was the SOHO spacecraft orbiting the sun, right? But our friends, Seth was my friend, before this, in California, were also aware that we were chasing this signal. And we went to bed in West Virginia and forgot to tell them that it wasn't real. So they stayed up until the star rose again at 2 in the morning. And so we had some fences to mend when we got back home.
Do you forgive her, Seth?
It was a great test of the system.
It's a test of the system, but it also shows the role of confirmation in both your pursuits. That it's one thing to get a signal, or to get a signal that is a signature, or something that is very exciting. It's another thing to follow up on confirmation. Now, surely someone has a question who would like to come down to the microphone. But let me ask while people are lining up here. So now it's a lot of people. Good. So we have the technosignatures that Jill has outlined, and we have what Vikki has been talking about, biosignatures. But I wonder if the signature could come from another source altogether. NASA's Mars 2020 rover is going to gather samples for a return mission to Earth, and it's looking for signs of past life. And if it does find that, does that count as biosignature?
Yes, absolutely.
Okay,
yeah, we call those in situ biosignatures. They're in the rock, right?
Okay,
So
even
what
if
I
it's
do
in
are
the rock.
astronomical or exoplanet biosignatures.
Okay,
Yeah.
all right. Yes, sir.
This is for Jill. So when you talk about signals, a radio signal of some type, electromagnetic signal coming in, my understanding is until maybe 60 years ago, most of the signals were AM, so they bounced across the atmosphere. So very little probably got out into deep space. So maybe it's the last 60 years. Now you look at where we are today, there's probably less radio signatures maybe today than 10 or 15 years ago, because we're using fiber optic. Most things are pointing towards the Earth now. So an advanced civilization may have a very, help me on this, in terms of a short window, 100 years, 200 years, where there's some sort of major broadcast of electromagnetic waves. So with that in mind, maybe comment on it, alternative ways of thinking about technosignatures, given that, et cetera.
Yes, our broadcast apparatus is going away. We're doing the satellite broadcast, but those actually have a back lobe. It's much, much smaller, but you can still see it if you have a strong enough telescope, a big enough telescope. But in fact, we might be fortunate enough to have someone out there setting up a deliberate beacon. It might not just be the leakage from their consumer electronics. There might be deliberately maintained transmitters.
Thank you, both of you, for the great talk. This is for Vikki. How much interface do you have with people who are researching the idea of what's called a shadow ecology here on Earth, and how does that affect the work that you're doing?
So the shadow biosphere idea, I actually interacted with Sarah the other day. Yeah, we do. That was posited as an idea.
Do you want to explain it?
Can you give
Okay, so
just
that's
a
all right. So the
quick-
shadow biosphere, if I understand it correctly, is this idea that there may have been an independent origin of life, but it's life in such a form that we can't actually detect or even recognize it. The shadow biosphere exists, but we are unable to recognize that it is life. The only problem with that is until we can find a way to test it or discover it, it's not really science in that sense, because I can't do an experiment to learn more about it. So it's an interesting idea, and it's certainly, again, trying to understand what our ignorance is. It's an interesting idea to pursue, but for me, if you're going to posit a shadow biosphere, you need to at least tell me what observable I should be looking for to try and verify that it exists.
Usually when we talk about Goldilocks zones, they're in terms of the temperature the planet is experiencing. But what about the size of the planet? How small can a planet be? How big can a planet be and be able to develop life?
So
Okay.
What are the characteristics of a habitable
Yeah,
planet?
habitable
Well, it
planet.
could be even microorganisms.
Right.
Right.
And maybe just one line of what the Goldilocks zone is for anyone whose mind is slipping to porridge and other things.
Oh, okay. So, so the Goldilocks zone or habitable zone is again that region around a star where we think if we put an Earth-like planet in that position, it would be able to support liquid water on its surface. So we would get that light on water that we're looking for. And so the size of the planet, essentially, we can, okay, so there's a number of things. Whether or not a planet is habitable depends on a zillion factors. I don't have time to go into all of them, but one of them, obviously, is retaining an atmosphere and retaining an ocean, being able to hold on to that. Mars has not been very good at that. Mars is in the habitable zone. It has not been able to retain a dense atmosphere and an ocean over time, and so you could take that. So it's a tenth of the mass of the Earth, for example. So that's one limit. And then for the too big, this is really interesting. So we have a bunch of exoplanets now, so we've been doing statistics. And so we now have plots of size and mass for a bunch of different planets, and we found empirically, so by measurement, that basically anything that is smaller than 1.5 Earth radii is likely to be rocky. Anything larger than 1.5 Earth radii probably has a dense hydrogen envelope around it, which would make it difficult for it to be habitable. So we now have this kind of cut at 1.5 Earth radii that says, okay, probabilistically, if we see something within, 0.5 to 1.5 Earth radii, that's kind of the zone we would be looking in for atmospheric retention. And yeah, so you don't lose your atmosphere and you don't gain too much atmosphere on the other side.
Just right amount of
Just
atmosphere.
right.
I think this, we'll see if we can get through everyone. The gentleman who just came in at the very one, he's putting his hands together like, please don't stop me. I think we'll try to get through everybody, but that'll be it. So
Right, so
we'll
we'll go
try to go
fast.
at a
Yeah.
Thank you
swift
for
pace.
Speed round.
thank you for presenting this information and knowledge. And I would like to ask about an article I read a couple years back, vague on the details, but there was a star survey, several million stars in a small area, and they picked out maybe 100 that had some sort of optical communication, possibly evidence of some specific frequency of light that was unique. Do you recall that, and is there any follow-up on that area?
Did everyone hear that question? It was a little faint. Okay, go ahead.
I think the area on the sky that you're talking about is the 100 square degrees that the Kepler spacecraft searched for exoplanets. In terms of a claim that for something like 100, there was some evidence of optical communication, that's where I'm losing you. I don't remember ever hearing that.
Well, maybe you didn't read the article, and maybe it was not a valid article. I think that's what I was looking for. Thank you.
Hi, I have two questions. The first is probably pretty easy to answer. The second, I'm probably going to be that guy. But the first question is, what is the status of Tabitha's star, the star that was losing brightness?
That's Boyagin's star.
Boyagen, I'm sorry.
Right? It's not, Tabby is a little bit
Okay.
rude.
I'm sorry. Well, I mean, I've heard it.
Boyagin's star. If she were a man, you would have used her last name to name the star. Lots and lots of follow-up observations are being done continuously, and there have been a number of events, and they now have enough different wavelength color information, so it's pretty clear that it's dust is what's causing those obscurations, dips in the brightness.
And then the second question is, do you think that there's any reason to give validity to the reports in the New York Times from 2017 about the UAPs? Do you think that that's something that we should pay attention to, or do you think it's just complete garbage?
Well, you faded out there. I didn't
Sorry,
hear.
in 2017, the New York Times basically came out and said that the military had been observing UFOs. And I was wondering if you guys thought that that was something that we should keep an eye on, or if it's just complete garbage.
People see UFOs all the time. Even the Navy sees UFOs all the time. They are just unidentified flying objects. It doesn't necessarily mean they have anything to do with alien spacecraft. So yes, we see things, and we've got millions of years of evolution in our brain that wants us to take something that we don't understand and label it as something that we think we understand. And so there's not been any evidence that links what's seen to alien spacecraft, including the Tic Tacs.
Well, while we're on that, just yes or no, that interstellar object of Muamua, alien ship or not? Yes or no?
No.
No, okay.
It's an ask.
There's still debate about it, but we just settled that now. Okay, yes, sir.
Thanks for the talk. And I just have a question with regards to the commercialization of space, if that's going to affect land-based astronomy. I think the recent stat with SpaceX's Starlink is they have permits for 10,000 microsatellites, and they're applying for permits for 30,000 more. And the current number of satellites in orbit is around 6,000. So as the commercialization of space progresses, how is that going to affect land-based astronomy?
Yeah, I think it's a tragedy of the commons and about to happen, right? We have so much space junk up there that in sun-synchronous orbit at certain altitudes, even if we never launched another thing, you'd get runaway collisions. We're almost at that limit. So there's going to have to be a lot of cleanup done. And all of those spacecraft that are going to be launched need to have really good end-of-life plans to deorbit them or boost them higher up where they won't be a problem. Right? Otherwise, we'll lose launch capability. We won't be, the stuff will be so thick, we won't be able to safely launch.
And from the astronomy perspective, people say, oh, well, yeah, well, it ruins ground-based astronomy, but you can just, build space telescopes. But if we can't get through the debris, that would be bad. And secondly, our telescopes on the ground are massive. They're much bigger. We can build much bigger things on the ground than we can launch into space. I mean, that's a pretty straightforward thing to understand. So losing the capability of, for example, these super large telescopes we're building right now would be catastrophic. So, I mean, astronomers being who they are, we're sitting there trying to figure out, okay, algorithms, how do I de-Starlink my data, for example? So we can try and take some of this stuff out algorithmically, but it is not, we're not happy right now. So.
Here we have 2 more questions.
When you find extraterrestrial intelligence, if you could, would you try to find them and meet them?
Would I try and eat them?
Find them and meet them.
Find them and meet them. I don't know, I think we like your first question. Would you try to eat them? Okay, but that's for after the show, we'll discuss that. Would you try to meet them?
Or try to meet them.
I thought you said yes. I would definitely be very interested in meeting them because I think the only way that we're going to understand biology is by finding a second example of it, right? Mm-hmm. So when you have something unique, you have only one example. It might well be unique, but the moment that you find a second example, you know that whatever it is ubiquitous everywhere. So I would very much like to meet this alien in order to understand if there's any other way of making life and biology.
And I would say the same. And also just the evolution of intelligence, different types of intelligence as well. As a scientist, I'd be fascinated by this alien to try and understand and to maybe learn more about their planet and so on. And they'd have a first-hand account, obviously, so that would be another way of learning some actual planetary science that I couldn't do otherwise. So I would love to meet that alien, yes.
It's a great question. Would you like to meet the alien?
Sure.
And we have one last question.
All right, cool. So yeah, I guess on the same thread as aliens, right? So you mentioned this is like 12 parsecs away or something like that, and that's like 36 light years, I think, give or take. So even if you were to find life, right, and you mentioned it was like an 80% confidence interval or something like that, is there a way to, I guess, have, I don't know, like just more confidence with something at such a vast distance? Because I don't know, it seems like relatively easier to check out Enceladus or something, right, and see. So I don't know if there's any techniques in the works or anything like that.
Yeah, absolutely. And I mean, yeah, it'd be easy to check out Enceladus, certainly, but the probability that Enceladus has life is probably less likely than, say, one of these things with an ocean on it. So we're always trading
but
these.
Enceladus has an ocean.
Enceladus has an ocean, yes, and it is spewing into space, which makes it easier. Again, there'd be subsurface life there, but if we can find abundant life on the surface of a planet interacting with its biosphere, it's much easier, to find it that way. But what we would try to do is we would try to learn how to make the next observation that would increase our confidence. And so, if we found something that looked suggestive, believe me, every telescope on the planet, and Jill's as well, will be pointing, to that object. And so we will, as scientists, bootstrap our way up to figure out, okay, what's the next measurement we need to make to test the theory that this is life or this is not life? And we will keep doing those experiments until we increase our confidence.
Thank you. Right, well, we're winding up, so I just want to say thank you to Dr. Jill Tarter and Dr. Vikki Meadows. Thank you for joining us this evening. And did you want to conclude with a monetary wager? Okay.
That would be appropriate because it's all down to luck at this point, I think.
Anyone wants to take bets or engage them in sorts of bets? Which will come first, technosignatures or biosignatures?
How about asking the audience, how many of you believe that we are not alone? How many of you believe we are alone, that this is it? Oh, we have a couple. All right. You want to stay on for the follow-on lecture. So, and how many are sided with the technosignature being the first evidence that we will get? Okay. And how about the biosignature? More on the biosignature side. Okay. So Jill invites you to stay on for the follow-on lecture as well. So anyway, I would like to join Molly in thanking Jill and Vikki for a wonderful session. I would also like to thank Molly for her brilliant moderating of that session.
Yes.
I would like to thank our incredibly well-behaved audience and questioners who kept their questions short, lined up. We got it all done on time. The answers were brief. What a professional group this is. Absolutely amazing. So thanks to all of you as well. And I do want to say that, as goes with tradition, our guests tonight get the highly coveted SETI Talks mug.
Oh, cool.
And patch that goes with the mug. And when I say highly coveted, these go for millions on eBay. So, these don't take them lightly. But we're very grateful to Vikki and Jill and Molly for this wonderful and engaging talk. We hope you found it inspiring and interesting and maybe just increasing your curiosity, if nothing else, and especially for those of you who are here for the first time, we hope this is enough of a teaser to bring you back for more. The SETI Talk series will be interrupted in December because of the holidays, so we won't. I'm wrong. Update.
I think it's December 17th, but it will be on our website.
Okay, so I stand overruled. And happily so. So that's great news. So because the talk is not yet on our website, but our website, SETI.org/SETI Talks, is where you can go to find out about these lectures. And not only find out about the upcoming talks, but also all the past talks. And we literally have hundreds of these talks and lectures on our YouTube channel, cleverly also called SETI Talks. And you can see them. And there's amazing array of topics and speakers and brilliantly inspiring information on that site. So please get to know us on SETI.org, get to know us on SETI.org/SETI Talks. Listen to Big Picture Science and hear more of Molly and Seth and their amazing guests. And once again, happy anniversary to the SETI Institute. Congratulations, Jill, on 35 years of inspiring science. And also, one of our trustees, Andy Fracknoy, where's Andy? Andy here has been on the board also since the very beginning. He's 150 years old, but just amazing. So thank you, Andy, for being here tonight. Thanks, everybody, for joining us, and we'll see you next time.